Good evening. Before we begin our main theme tonight, there are some very interesting news notes. First of all, the unmanned Russian spacecraft now in orbit round the planet Mars. Its main task is to study Phobos, the larger of Mars's two tiny satellites, and it is in fact sending back pictures. Phobos is a curious little world, shaped rather like a potato, and cratered and furrowed. But also on board this probe is an experiment masterminded by the Irish scientist, Professor Susan McKenna-Lawler. And this is a charged particle experiment. And it looks very much as though it has detected charged particles in orbit round Mars, of the same kind as our own Van Allen zones, although very much weaker. And if this is true, and I think it probably is, then it may well indicate that Mars does have a magnetic field. But I suppose the real interest is going to come next month when the probe actually latches onto Phobos itself. That's going to be fascinating indeed. And then, very much nearer home, to the moon. Many people have maintained that the moon is totally inert and changeless. Well, practical observers, such as myself, have never agreed with this. We report, now and then, short-lived transient phenomena, glows and obscurations. They are not easy to see, and they are very difficult indeed to confirm photographically. But we now have an excellent photograph of a lunar phenomenon not far from the crater Proclus. And there it is, that flare near the top of the picture. And this was taken by the Greek astronomer George Kolovos. And I think all photographic results have now been eliminated. It's genuine, all right. And almost certainly is due to gaseous emissions from below the lunar crust. And that's very important. And then we have a really huge sunspot, the biggest for many years. And this photograph was taken specially for our program on Saturday, March the 11th, by Douglas Arnold. And there's the spot near the top of the solar disk. It really is huge. And it is in fact visible with the naked eye. But do let me warn you, please, whatever you do, don't stare at the sun, even with the naked eye. You may damage your eyes. And whatever happens, don't look straight at the sun through any telescope or pair of binoculars, even with a dark filter. If you do, you're going to destroy your eyesight, and this has happened. But the spot is certainly there. It's also very active. It's sending out charged particles and shortwave radiation. And these very often cause aurorae or polar lights. And there was one very misleading report earlier on this week, and it was said that the spot must produce a brilliant aurora. And I gather some people actually drove north to North England or even Scotland hoping to see it. Well, of course, that's quite wrong. You cannot forecast aurorae. This spot may well produce displays of aurora, I don't know, but you can't guarantee it. All I'm saying is that we may quite easily have some aurorae in the next few days. If not, please don't blame me. And now, on to our main theme. And we're coming back to the large cloud of Magellan, which unfortunately is too far south to be seen from here. It's a separate galaxy. Our own galaxy is shaped rather like two fried eggs clapped together back to back, and the sun is well away from the center, and that's shown here near the bottom of the picture. And the distance of the large cloud is 170,000 light years, so we're seeing it as it used to be 170,000 years ago. And there, in February 1987, there was a huge stellar explosion of the kind known as a supernova. And I couldn't resist taking a trip down to have a look at it, and there's my picture. You can see the supernova right in the middle. It's not a very good picture, but it was taken with an unguided hand camera, and I just hand-held it. Well, the supernova is in fact still there, but it's no longer visible with the naked eye as it was when I observed it. And after all, the last naked eye supernova in our own galaxy was seen as long ago as the year 1604. There was one in 1885 in the Andromeda spiral, which reached the fringe of naked eye visibility, but that was what's called a Type 1 supernova, involving the total destruction of a white dwarf star, which literally blows itself to pieces. Well, the supernova we've just seen is in fact a Type 2, and there was an example of a Type 2 supernova in the year 1054, and that's resulted in the patch of dust and gas that we call the Crab Nebula, 6,000 light years away. Well, when the supernova blazed out in 1987, the question was, would it produce a pulsar, or would it possibly even produce a black hole? Nobody knew. Everyone wanted very much to find out. Now, just before our last Sky at Night program, there was a report from the Cerro Tololo Observatory in Chile. And there's a picture of it. And inside that main dome is the 4-meter telescope. And observations with that reflector indicated that a pulsar had been identified in the supernova remnant in the LMC, Large Magellanic Cloud. Well, now, we are not quite so certain about that. And at this stage, we are delighted to welcome yet again one of our old friends, Dr. Paul Murdin of the Royal Greenwich Observatory, Westminster. Welcome back, Paul. Now, what's the latest news on this?
The latest news is that the pulsar was only seen on the one occasion in the middle of January at Chirotololo, and that subsequently the same team that identified it have looked for it and not seen it since. And indeed other astronomers in the Southern Hemisphere at the European Southern Observatory and in Australia have also looked for it and failed to see it. But I think we have to take the observations made by a very experienced team at their face value so far. We wait for confirmation, of course, but we'll see exactly how to go ahead and analyze the data which they've produced. Now, what they actually saw was data which they had fed from the 4-meter telescope into their computer, which then analyzed the data for periodic fluctuations. And periodic fluctuations are indicated by the very big spike which there is in the lower part of this graph of the power spectrum from the supernova. When the computer reconstructed the light curve on the basis of that information, it produced a double flashed cycle. There are 2 flashes separated by 0.2 of a millisecond, repeating every 0.5 milliseconds. So a double flash repeating 2,000 times a second.
Because we still don't know definitely if the pulsar is there. And, I mean, why has it taken nearly 2 years to find out?
Well, the pulsar has been produced inside the middle of the supernova, and the supernova is a very big explosion of the body of the star. And for 2 years, astronomers have been watching while this explosion gets larger and larger and larger and larger, and becomes more and more transparent so that they can see right through the explosion into the middle. They've been, as it were, peering through the fog in order to see whether the supernova produced this neutron star or a pulsar or a black hole. And it may be that the reason why some people see it and some people don't is that the fog opened up in the middle of January and has closed in again, and we have to wait for it to dissipate. The first indications that a neutron star had been made came from on the very first day of the supernova outburst on February the 23rd, 1987, when astronomers detected a neutrino burst from the Magellanic Cloud. And the neutrinos are the signature which astronomers had all expected to come from the formation of a neutron star.
Well, what exactly is a pulsar? I mean, it's made up of neutrons, but what are its main characteristics?
A pulsar is indeed a neutron star, which is the mass of the sun condensed, in fact even slightly more than the mass of the sun, condensed down into an object which is no larger than the city of Greater London, say 10 or 20 kilometers in radius. Now that means that the material in it is compressed to an enormous density. We're talking about densities here of 1 million tons per cubic millimeter, or to put it a little bit more graphically, a pinhead like this one would have the same mass as the biggest of the supertankers that's been produced. The neutron star is formed by the collapse of the core of a star, this star which inhabited the Magellanic Cloud. The collapse released an enormous amount of energy which was responsible for the blowing apart of the star and became then the supernova which we've experienced for the last 2 years. But when the core collapses and shrinks, any rotation which the core has got is sped up, perhaps 1 millionfold. And if the core of the original star had a rotation period of 10 minutes to an hour, then the neutron star, which is formed by the collapse of the core, has a rotation period of a millisecond or so. The principle is exactly the same as the principle which makes an ice skater spin very quickly as he draws his arms closer to his body in the final pirouette of his routine. He gets very much faster as he contracts himself. And it's the rotation of the neutron star which is the clock which drives the repetitive flashes. The flashes themselves are caused by some lighthouse-like beams which are on the neutron star. For some pulsars, the lighthouse beams pass through the Earth. For some, they don't, and we never see them. But if the beams do pass through the Earth, they flash repetitively as the neutron star rotates once every revolution. Now, this speed of rotation won't actually remain the same forever. Astronomers believe that neutron stars are formed rotating quite quickly in a supernova explosion, but just as the Earth in geological times had a rotation period of 23 hours, and now it's slowed to 24, so also fast pulsars slow down. We know, for example, that in the Crab Nebula, which was a supernova that took place 900 years ago, a pulsar was formed which now has a rotation period of 30 times a second. It flashes 30 times a second at us. In the case of the Vela supernova, which was unseen by any people who recorded it 10,000 years ago or so, that has a pulsar in its interior which flashes 11 times a second. So pulsars are born fast and gradually slow down to over 1 million or 10 million years to a rotation period of perhaps once a second. Now, that's not the only way in which fast pulsars can be formed. There's another way which takes an old pulsar and makes it go faster, speeds it up. These pulsars are called the millisecond pulsars, and examples of them have been discovered in various places over the last few years. And the story about how it is they actually have come about has recently sort of become clear. There's an interesting example of such a pulsar in a globular cluster called M4. A globular cluster is a cemetery of old dead stars, and there haven't been any supernovae of the sort that form neutron stars in a globular cluster like this for many millions of years, tens of millions of years or more. But there have been, presumably, lots of supernovae in that globular cluster a long, long time ago, and there are therefore lots and lots of neutron stars in it, even though they're old ones and mostly we can't see them because they're old and dead. But as these neutron stars wander around in amongst the stars in the globular cluster, in and out, looping round in orbit, it may be that from time to time one encounters a star and gets hooked onto it. It will get near and get captured and form a double star. And you get a double star, which is one of the stars of the globular cluster with a pulsar companion. Now, the story can develop from there, in fact, because the globular cluster star can age, get old, evolve. It can turn into a red giant and expand and get larger. And the expansion may, in fact, push material over from the globular cluster star onto the pulsar in a stream of gas. This stream of gas is very tenuous, not much sort of mass in it, but there isn't much sort of impact in the jet of air, which I'm going to blow through this straw, and yet I can make this ball spin very quickly as the jet of air strikes the surface.
Yes, very graphic.
Well, we've only spun that pulsar up to a 1 rotation per second, but in M4 the pulsar spun up to 1,000 times per second.
And when this happens, presumably the pulsar itself becomes a great deal more energetic.
Yes, it regains some of its rotational kinetic energy and generates a lot of energy into the surrounding region around it, and can shine very brightly onto the companion star and heat the nearer face, the face that is towards where the pulsar is. And then as the double star rotates in its orbit, we can get presented with the hot face, the face that's towards the pulsar, when the pulsar lies between the Earth and the globular cluster star, and then the cold face as we see the back of the globular cluster star. So the globular cluster star will brighten and then fade again. An example of this sort of pulsar and this sort of phenomenon in a binary system has been discovered last year by the William Herschel telescope on La Palma. The star which it discovered winks on and off among 4 other stars in the field as we see the hot face and the cool one. Now this energy, which is boiling the nearer surface of the companion star, can be so large that the star itself can be literally boiled away. It evaporates. It gets smaller and smaller and smaller. And the amount of wind that blows from the surface of the globular cluster star spreads out into the interstellar material. And as the star passes through the interstellar material, it leaves a wake behind, in the same way that a speedboat leaves a triangular wake as it passes through water.
So in the end, the star that captured the pulsar is completely destroyed.
It's literally boiled away, and eventually the pulsar will find itself on its own again, a lone star wandering about in space, because it has destroyed its companion.
In the case of cosmic murder, how long does it take?
It will take something like 10 million years for this actually to take place.
Well, it looks very much then as though not all these millisecond pulsars are due to the collapse of a supernova.
No, some of them are formed by this second mechanism, but obviously in the case of the obviously in the case of the pulsar in the Large Magellanic Cloud supernova, it must have been produced by this collapse mechanism, if indeed the observational reports are confirmed and there really is a pulsar there. This pulsar is going so fast, 1,968 revolutions per second to be more precise, that the speed of the equator of the star is very nearly equal to the speed of light, roughly half the speed of light. The equator can't move faster than the speed of light, of course, and so we can actually set some limits to the size of the pulsar. For example, if it was possible for a car to travel at the speed of light around the M25 orbital motorway around London, and I think such a thing would be very unlikely, then the car would be going around the M25 2,000 times per second. So the pulsar must fit within the M25. Its radius must be less than about 25 kilometers.
Well, it's quite fascinating. What are the latest developments, Paul?
Well, one rather surprising result from this pulsar is that its period, although quite precise at 1,968 cycles per second, is not absolutely precise. There's a little wobble in it. And it appears that there may be some object in orbit around the pulsar pulling it to and fro, possibly something the mass of Jupiter, a planet-like object maybe.
Well, I find that rather difficult to believe. And what about the mystery spot? Hasn't that reappeared?
Yes, the mystery spot was an object which was seen in a few months after the outbreak of the supernova, very, very close into the supernova, and now has been rediscovered, this time much further out, about 1 arc-second away.
I wonder what it is. Well, Paul, what's going to happen in the end?
Well, in the end, the explosion gets larger and larger and larger and dissipates out to nothing. The supernova loses its identity in the Magellanic Cloud, and in the center of the place where the supernova remnant was will be a neutron star rotating very slowly, a cold, dead cinder of a star which will wander about forever, cold, dark matter in the Large Magellanic Cloud.
Well, it's an amazing prospect, and I suppose before long we'll know definitely whether there is or is not a pulsar inside the Large Magellanic Cloud. Paul, thank you very much.
Thank you, Pat.
We've simply got to wait to see what happens next. Meanwhile, for our next Sky at Night, we're going on a journey. I invite you to come with me to the Atacama Desert of Chile to visit there the Observatory of La Silla, high up in the Andes. So I hope you'll join me then. Meanwhile, from Paul and myself and the Large Magellanic Cloud, good night.